My name is Farsane TABATABA-VAKILI. I'm currently a postdoc at LMU in Munich, and soon to be probably assistant professor in TU Braunschweig in northern Germany. So if anybody, is looking for another postdoc position, and may or may not have money, I don't know. I said I have to fill these 25 minutes. All right. So we've already gotten a very nice introduction from Mike about this material, chromium sulfur bromide. So first of all, let me tell you something that you already know. There are many very exciting van der Waals crystals. We have, of course, the most famous is graphene, individual sheets of carbon, which are essentially a metal. We have insulators, such as hexagonal boron nitride. We have semiconductors, such as transition metal like aquagenides, molybdenum diselenide, tungsten disulfide, this kind of stuff. We have ferromagnets, such as chromium triiodide, chromium tribromide. And now, tada, we also have a magnetic semiconductor. I mean, there's more than one, but there's one that we all love, which is chromium sulfur bromide. I'm preaching to the choir, but right. So why is chromium sulfur bromide interesting? Many reasons. For me, as an optical spectroscopist, it is because it is both a direct bandgap semiconductor that hosts van der Waals excitons, as well as a layered A-type antiferromagnet. And so looking at the band structure here, the red dots, the DFT plus GW, we have a direct band gap at the gamma point, and then we have nearly flat bands along gamma X in the conduction band and highly dispersive bands along gamma Y. So the material is also quasi-one-dimensional. And we have two conduction bands that are very closely spaced in energy, which is going to be important later on when we look at our model. Then it's a layered A-type antiferromagnet. So the monolayer is ferromagnetic with the magnetic moment along the in-plane B axis, and then the interlayer coupling is antiferromagnetic. We have a magnetic easy axis along the B axis and a magnetic hard axis along the out-of-plane C axis. So since this is a workshop about magnetism, I thought I would introduce this guy to you. So we are optical spectroscopists. We care about excitons. Excitons are correlated electron-hole pairs. They're of van der Waals type, so that means they're quite large with respect to the lattice structure. And so one thing that for us is very cool about CrSBr is that the excitons are correlated with the magnetic order. So this was nicely shown in this work by Nathan Wilson and co-workers from a few years ago, back when he was with Xiaolong Xu. And so if we apply a magnetic field along the in-plane B axis, we observe a sudden jump in exciton energy here. This is photoluminescence at a critical magnetic field where the magnetic order changes from in-plane antiferromagnetic to in-plane ferromagnetic. And if we apply a magnetic field along the out-of-plane C axis, we observe a gradual spin canting from in-plane antiferromagnetic to out-of-plane ferromagnetic, characterized by a parabolic shift in exciton energy. So this is very cool from a spectroscopist's point of view. And then there's been a lot of other cool stuff happening. So there've been demonstrations of exciton-magnon coupling here in this work, for example, from just a couple years ago, using probe spectroscopy and canting the spins a little bit with an out-of-plane magnetic field, and looking at the transient spectroscopy, transient reflections, they were able to observe these oscillations, which are a hallmark of exciton-magnon coupling. And then Florian here in this very nice work, he demonstrated polaritons for the first time in CrSBr, and then also showed polariton magnon coupling using the same method. So just to, the idea was to introduce this material a bit, but somehow you're all working on it, so. All right, so what did we do? We looked at few layers, CrSBr mono, bi, and tri-layer, and we gated the material for the first time. So we built single-gated field effect devices. They were supposed to be dual-gated, but as for those of you who've worked with gates, one usually doesn't work. So the flake is sandwiched in hexagonal boron nitride. We use few-layer graphene as a top gate and contact layer. This is an optical image of a heterostructure. And so with this gating, we can charge up the material. So the goal is to see trions and to doping control the properties of this material. And here is an image of the low temperature differential reflectance, which gives a measure of the absorption. And here blue color indicates regions of strong excitonic resonance, and the diamonds are the regions on the sample where we performed our measurements. So let's start with the monolayer. So another thing that I find quite curious about this material, in contrast to transition metal decacrogenites, where it becomes interesting in the monolayer, here the monolayer is kind of boring from an optical point of view. So let's look at the differential reflectance and the photoluminescence. So here we observe one weak excitonic feature, which we call XA. And as we apply a gate voltage, we just observe a very small redshift of XA. So no clear signs of charge doping. And we have basically no Stokes shift, so this looks like it is a direct excitonic transition. Then, moving to the bilayer, things get more interesting. So in the bilayer, we also see this XA feature at roughly the same energy. And then at around 20 MeV blue shift, we observe a very strong excitonic resonance, which we label here as XB. And then as we apply a gate voltage, XB becomes weaker and transfers its oscillator strength to a negative trion or Fermi-polaron here at around 19 MeV redshift. So this is an exciton plus another electron. And we observe the same thing in photoluminescence. And we're only able to N-dope, we're not able to P-dope. We don't know exactly why. Maybe it's because our contacts are so bad, or because you just actually cannot P-dope the material, or it's already intrinsically highly N-doped, many possibilities. Then in the trilayer, in addition to all of the features that we observe in the bilayer, we observe a second neutral exciton, labeled here as XB prime, at around 5 MeV redshift from XB, and XB prime, curiously, does not show any signs of charge doping. So you see here, it's just a straight line for this entire doping regime, no trions. All right. So all of these excitons have an in-plane polarized optical dipole with out-of-plane emission, which we can see here in these k-space dispersions. So we have highest intensity at small in-plane k vectors, and they're all highly linearly polarized, which we can see here in these polarization-resolved measurements. So basically, the entire emission goes along the b-axis and no emission along A. So this is also because of this quasi-one-dimensional character, because of this anisotropic band structure. Now, let's apply a magnetic field, starting with the out-of-plane c-axis. So here we observe this gradual spin canting with the parabolic shift in exciton energy. And we can see here, so we see this for XA, for XB, and also for XB minus, although the dispersion is a bit flatter for the trion. And we're able to model this, so this was my colleague Anva sitting in the back who did the modeling. So in our model, we take intra- and interlayer exciton coupling into account, which gets, via hole tunneling, which gets turned on with the magnetic field. More about the model in a bit. Now let's have a look at the trilayer. So here, this other neutral exciton XB prime shows a factor 2 in curvature, and we're also able to capture this in our model. So let me tell you about this model. So we believe that XA and XB are two distinct intralayer exciton species formed with these two conduction bands, so XA with the lower energy C1 conduction band and XB with the higher energy C2 conduction band. And then, as we apply a magnetic field, XA and XB couple to their interlayer exciton counterparts via hole tunneling. This is described in our Hamiltonian in these blocks here, where SB is the coupling term with magnetic field. And then, as we dope, XB can form a trion by binding to a second electron in the lower energy conduction band. So we believe that the Fermi C, in our case, lies in C1 with no additional charge in C2. And this is also why we do not observe any trions of XA, because these would be Pauli forbidden, because we cannot have two bound electrons in the same conduction band due to the spin polarization. And then In the trilayer, we believe that this xp prime stems exclusively from the middle layer, and that the energy shift comes from the different dielectric environment, and the factor 2 in curvature stems from xp prime being able to couple to 2 interlayer excitons. And then, curiously, we do not observe any signature of an xa prime, so it seems like we don't have any signature of the C1 conduction band, which could be because it shifts to higher energy, the band structure changes, or something else. If you have any ideas, please let me know. So another indicator of there not being any C1 band is that we're not able to dope this xp prime. So it seems like the charge lives only in the outer layers. So we're only able to dope the first and the third layer. And here is a bit of a summary of the model parameters. So we assume a large interlayer energy difference in the order of 50 to 100 MeV, much larger than the Fermi energy and the trion binding energy. Fermi energy is 10 MeV, trion binding energy is 19 MeV, and by fitting our model to the experimental data, we get a whole tunneling parameter of 2 MeV per Tesla squared. Here are the eigenvalues of the Hamiltonians on the previous slide, and this is how they look like. So this matches very well with the experimental data. So we have a model that self-consistently describes our observation A. Now, let's apply a magnetic field along the in-plane B axis. So here, we observe this abrupt jump in exciton energy at a critical magnetic field where the spin slips. We see this again for XA, XB, and XB minus. And then, in the trilayer, we observe another curious intermediate state here, where only the energy of the lower exciton here jumps. So here we believe that we have a state where the spin of only one layer flips, such that we have two adjacent layers with ferromagnetic order and two adjacent layers with antiferromagnetic order. And this critical magnetic field of the spin flip transition shows a doping dependence and also a hysteresis. So if we reverse the magnetic field direction, the critical field is a different value, and then if we dope, we see that this hysteresis loop here shifts to smaller magnetic fields. And this is because the interlayer exchange energy is inversely dependent on on-site Coulomb interaction. So as we dope, we increase the Coulomb interaction, and with that, we reduce interlayer exchange energy, and with that, we reduce the critical magnetic field. And similar results were shown a few years ago in chromium triiodide, where they also showed a doping dependence of the magnetization. So plotted here is the critical magnetic field as a function of gate voltage. And now if we cross this line horizontally, so if we dope at a given magnetic field, we can also induce this metamagnetic transition quasi-electrostatically. So here this is shown in the bilayer. If we're at 165 millitesla, we then apply doping, and we see here this jump in exciton energy at around 0 volts, where we have this change in the magnetic order. And in the trilayer here, this is shown for the antiferromagnetic to intermediate state transition. So this is just kind of neat. So we have a kind of one-way electromagnetic switch. And now let's have a look at the spin lattice energy to get a better understanding of when which spin slip occurs. So in the bilayer, the situation is relatively simple. We have two antiferromagnetic states which are energetically degenerate and two ferromagnetic states. If we now start off at a negative magnetic field and increase the magnetic field, we start off in the ferromagnetic state, we continue along this curve. At some point, we cross these antiferromagnetic states. We need a little bit of extra energy to flip the spins. This is where the hysteresis comes in. Then we're in the antiferromagnetic state, cross the other ferromagnetic state, bit of extra energy, flip the spins. Quite simple. Then in the trilayer, the two antiferromagnetic states are no longer energetically degenerate, and we have these additional two intermediate states here. So again, we start off in the ferromagnetic state here at a negative magnetic field. We transition to one of the antiferromagnetic states with just a spin of one layer flipping. Then at 0 Tesla, The other antiferromagnetic state would be energetically favorable. However, it would require the spins of all three layers to flip simultaneously. So this doesn't happen immediately. Instead, we continue along this curve until we cross one of these intermediate states and the other ferromagnetic state. And then with just the spin of a single layer flipping, we can transition to this kind of metastable intermediate state. And then with another 2 spin flips, we can relax down to the other antiferromagnetic state and ultimately to the other ferromagnetic state. So just to get a little bit of an intuition of why we have this intermediate state. Here I'm showing the bilayer with magnetic fields along the 3 different axes, or the material is anisotropic. So along the C-axis, we observe a spin canting with a saturation field of 2 Tesla. Along the A-axis, the intermediate magnetic axis, we observe a similar thing, but with a smaller saturation field of only 1 Tesla. And along the B-axis is the sudden spin flip transition with a critical field of only around 150 millitesla. And then in photoluminescence, we observe that in the antiferromagnetic state, the photoluminescence is very bright, but in the ferromagnetic state, it nearly vanishes, while the oscillator strength remains nearly identical. So we have, it seems like the population relaxes into some dark state. Also quite curious. And similar things for the trilayer, just with a larger critical field along the B-axis of around 300 millitesla, and then this increases further as we go towards the bulk. And then, so since the exciton energy is correlated with the magnetic order, we can use this to kind of all optically image the magnetism in this material. Very indirectly, of course, but so what I'm showing here are raster scan differential reflectance measurements of a small area of the bilayer of around 5 by 4 microns, where color-coded here in purple is the exciton energy in its antiferromagnetic state and in orange in its ferromagnetic state. And so we're just going along the sample step by step with our nanopositioners and measuring a DR spectrum in every position, and then just tracking the exciton energy here for XP. And so as we apply a magnetic field along the in-plane B-axis, we observe the nucleation of a ferromagnetic domain here at the edge of this bilayer region. Then as we increase the magnetic field, this domain expands and continues to grow until it ultimately encompasses this entire region here. And the corner here on the bottom left that flips last is close to the monolayer. And then, if we go to a magnetic field close to the critical field, so here 168 millitesla, and then we apply electrostatic doping, we observe the same magnetic domain formation across the metamagnetic transition. Just across a smaller range, because we have a smaller range accessible with doping. So, in this material, we can control the magnetic domain formation by both magnetic field and doping, which is kind of neat. And it's not very homogeneous, which may or may not be great, but at least it allows us to visualize this. Here, I'm showing another region on the sample where we have trilayer and adjacent bilayer, and the dotted line is the few layer graphene contact, which unfortunately goes right through the middle of this region. And in the trilayer, here we're tracking XP prime. And so as we increase our magnetic field, we observe here this intermediate state that nucleates at the edge of this graphene contact, and it expands with increasing magnetic field. And we can see that the intermediate state in the trilayer and the antiferromagnetic to ferromagnetic transition in the bilayer occur at the same magnetic field within resolution limit. So this is because these two regions interact via intralayer exchange coupling because these two regions share two of the same layers. So it happens together. They influence each other. And we can again also control this with doping. And here, I'm showing a larger sample region and all of these transitions. So we start off with this entire sample region being antiferromagnetic. The gray regions are areas where we have bubbles and other stuff where we can't really determine the exciton energy. And so, as we increase the magnetic field, we see here the ferromagnetic domain in the bilayer nucleates here at the bottom. It takes around 30 millitesla for this entire bilayer region to become fully ferromagnetic. We can also nicely see that, so here's the monolayer, we can nicely see that close to the monolayer, the spins flip last. And around here, 160 millitesla, the intermediate state in the trilayer starts to nucleate. It becomes fully intermediate, and then here it flips to the other antiferromagnetic state, and by around 300 millitesla, the trilayer starts to become ferromagnetic, and by 300 millitesla, this entire sample region is fully ferromagnetic. And so with that, I want to summarize by saying that we've observed tryons in bi- and trilayer chromium sulfur bromide for the first time. In the meantime, at least 2 other groups have reproduced these results. We've developed a model for the neutral and charged exciton multiplicity and dispersions, and we've shown doping-controlled hysteresis and switching of the magnetization, as well as identified an intermediate state in the trilayer, and we've shown large-scale optical imaging of the magnetism, and this work was just published in Nature Com about a month ago. And let me acknowledge everybody who was involved in this work. So this is our group at LMU. This is Alex, my PI. This is Anwar, who did the theory. Then Anna and Hui did some of the spectroscopy, and Hui and Tim built the samples. And collaborators, Misha Glazov at Joffe, who helped with the theory, Patrick Malatinsky at Basel, who helped with understanding the magnetism. We get very nice quality crystals from the Zdeněk Zofas group in Prague, and of course HBN from NIMS, and funding from the Munich Quantum Cluster, Marie Curie, and ERC. And thank you all very much for your attention.